right, welcome to 5 Minutes for the 5. We are looking at question number 4 from 2006. This is a mean value theorem Riemann sum question. They give you a rocket that's being launched with a positive velocity from time 0 to 80 seconds. At least that's what we're tracking here at the table. And they tell you that it's launched from a height of 0 feet. Here we go, part A. They want you to find the average acceleration of the rocket from 0 to 80 seconds and then indicate units of measure. Well, the first thing you want to be aware of here in looking at this question is they are giving you the velocity of the rocket and they want the average acceleration. Acceleration is the rate of change of the velocity. So what they're really asking you for here is the average rate of change of the velocity. So we're going to need to do the computation v of 80 minus v of 0 over 80 minus 0. So using the values from the table there, we're just going to be doing 49 minus 5 over 80, and that's going to result in 11 over 20 feet per second squared. That's going to be a 1-point answer for your 1 point given for the answer, and then also you have to make sure you have correct units for parts A and B here. So make sure you have feet per second squared also to get that second point. For part B, they want you to explain the meaning of the integral in terms of the rocket's flight, and then they want you to do a midpoint Riemann sum with 3 subintervals to find out the value of that integral or approximate it. So here we go. The explanation of the integral. You want to remember that since velocity is measured in feet per second, and the differential for time is measured in seconds, when you multiply those two together, you're just left with feet. So I know our answer is going to have to be something involving feet. And remember that all definite integrals compute a change. So we're going to be computing a change in feet, or in this case, the change in the height of the rocket from 10 to 70 seconds. So it would be written as this. The integral computes the change in the height of the rocket in feet on the interval from t equals 10 to t equals 70 seconds. You got to make sure you include the limits of integration, and you got to make sure you include the fact that it's measured in feet. The second part of the question is going to be the midpoint Riemann sum. You're going from 10 to 70, so we want to make sure that since we're going from 10 to 70, and since they want us to use 3 subintervals, that means we're going to be going from 10 to 30, 30 to 50, and then 50 to 70 as our 3 intervals. All right, because they're going to be equally spaced, and then we're going to be using the middle y value on each of those intervals to get the height that we use to kind of compute the midpoint sum. So when you put that all together, it's going to be the computation 20 times 22 plus 20 times 35 plus 20 times 44, because each interval is 20 units long with those given midpoint heights, and that's going to give you a final value of 2,020 feet. This full question would be worth 1 point for the explanation from the previous slide. Using v of 20, 40, and 60 is going to give you that second point. So did you kind of show this line here? That's the second point. And then the third point is the correct value of 2020. And also you're going to make sure you have the correct units of feet. All right, now the last part of the question is kind of the loaded question here. They tell you there's a second rocket B that's launched, and they give you the acceleration of this rocket. And they want you to find out which rocket is going faster at time t equals 80. Is it rocket A or rocket B? Well, you already know rocket A is going 49 feet per second at time 80. They tell you that right away in the chart, so you don't have to think about that one. But for rocket B, we're going to have to work our way back to the velocity function using the acceleration that they told us, and also the fact that the initial velocity of the rocket is 2. So we're going to put that all to use here. So to find the velocity, I know we can do the velocity at 0, and we can add to that the integral of the acceleration. All right, so for this question, it means we're doing the velocity at 0 plus the integral from 0 to 80 for 3 over the square root of t plus 1. We're going from 0 to 80 because they want us to figure out what's going on at time t equals 80. So you got to do some substitution here. U is equal to t plus 1, so du is going to equal dt. That's going to end up resulting in the following integral, v of 0 plus 3 times the integral from 1 to 81 for 1 over the square root of u. The 3 I factored out. I changed the limits of integration. Boom, boom, boom. Look who's here, Chet Loy. Change the limits of integration from 1 to 81, and just kind of following the integral steps here, you're going to get 3 times the integral from 1 to 81 for u to the negative 1/2 power, which is going to become 2 times u to the 1/2 power, and then the 3 kind of comes down for the ride. The 2 comes down for the ride. That's kind of holding its path here. You're going to want to multiply the 3 and the 2 together here. That's what I'm doing on the next screen here. So you get 6 root u, and you're going to evaluate that from 1 to 81. So when all's said and done there, you're going to get 50 feet per second for the value of the speed of the rocket B at time t equals 80. So when you compare the two answers, rocket B is going faster at time t equals 80 because it's going 50 feet per second versus rocket A, which is going 49. This is a 4-point question. It was 1 point for the antiderivative, which was 6 root t plus 1, or if you just had 6 times the square root of u there in the substitution, that would also be fine. The constant of integration in the initial condition, that's basically you're finding out that the velocity ends up equaling 50. You have to use the fact that they told you that v of 0 was equal to 2. They're going to want to know that you use that in some way, shape, or form. All right, when you're doing your work, there's a lot of ways to show that, but that's where that's coming from. And then your comparison of the two velocities. All right, this has been question 4 from 2006. Have a great day.